At the break of day, shafts of sunlight pour through the shallows of the Indo-Pacific, dappled and distorted by the shifting waves above. The reef wakes slowly but with purpose. Thousands of species rising from coral crevices, sandy pockets and sponge-covered ledges. Schools of anthias flutter like orange confetti through the water columns, while cleaner wrasses begin their morning shifts, flitting between moray eels and parrotfish in search of parasites. Crabs scuttle from under brain corals, and gobies hover inches from their burrows, scanning the blue for signs of motion.
And then, with the slow glide of dominance, enters Chilinus undulatus, the Napoleon wrasse.
At over 6 feet long and weighing close to 200 kilograms, this reef behemoth moves with the gravity of a tank, yet the grace of a dancer. Its lips are thick and protruding, resembling the muzzle of a bulldog, while the massive hump on its forehead, especially prominent in males, gives the species its name. In this maze of color and chaos, the Napoleonfish is impossible to ignore. It weaves through coral outcroppings without haste. There is no need for speed. Its mere presence carves out space. Smaller fish peel away instinctively. Predators rarely target something so large and armored, and few competitors challenge a Napoleon wrasse at its full size. Yet this animal is not merely a slow-moving heavyweight. It is precise, alert, and far more strategic than its bulk suggests. The Napoleonfish is a specialized predator, one of the few reef residents capable of cracking the armor of sea urchins, crabs, and even the venomous crown-of-thorns starfish. With powerful pharyngeal jaws hidden behind its front teeth, it crushes shells and spines with a violence that would shatter bone. But this violence is not indiscriminate. In the coral ecosystem, arguably one of the most complex and delicately balanced environments on Earth, such force must be applied selectively. When it hunts, it does so with method. A spiny lobster attempting to withdraw into a crevice finds its antennae grasped and body pulled out with a sudden, jarring burst of suction. A sea urchin, otherwise safe from most fish thanks to its rigid spines, is flipped over with a jet of water from the wrasse's operculum, exposing the soft underbelly. Then, with a few crushing bites, the spines are reduced to rubble and the creature is consumed. Crown-of-thorns starfish, notorious for devastating coral polyps by the square meter, are among its favored prey, a rare and ecologically important trait. Few animals touch the toxic spike-laden starfish, but the Napoleonfish does, helping contain their outbreaks. It doesn't eat them often, but when it does, the reef breathes easier. Despite its ability to consume tough, armored, and venomous prey, the Napoleonfish maintains a curious restraint. It does not devastate populations or clear out coral zones like some overzealous grazers. It is, in a sense, a blunt instrument of balance, an apex mesopredator whose limited numbers mean its influence is localized but deeply felt. It picks off the overgrown, the invasive, and the slow. It leaves behind an ecosystem not stripped bare, but trimmed and tuned. The territory it roams is vast, sometimes covering entire reef systems, especially in adult males. Juveniles stay in shallower lagoon areas, hiding among branching coral for protection. As they grow, their behavior changes, no longer avoiding attention but attracting it. Males begin to develop the distinctive hump and display territorial patrols, often chasing rivals with short bursts of speed. Fights are rare, but not unheard of. When two males do engage, it's a clash of jaws and mass that sends plumes of sand and debris into the water. Yet most conflicts are resolved with displays alone. Like many reef fish, Napoleon wrasses rely on color modulation and posturing to avoid bloodshed. Color plays an essential role in their lives. These fish are sexually dimorphic, with males showing intense blue and green hues with intricate facial markings, like fingerprint-like waves across the head. Females and juveniles often display more subdued tones, ranging from duller green to gray-blue. But color does not just reflect gender, it can change with age, mood, and status. Perhaps one of the most remarkable aspects of the Napoleonfish's biology is its reproductive strategy. It is a protogynous hermaphrodite, meaning individuals start life as females, and some transition to males later in life, often when a dominant male is removed or dies. This transformation is triggered hormonally and comes with physical and behavioral changes. Such flexibility allows populations to self-correct imbalances in sex ratio, a clever evolutionary trait in environments where mortality can be unpredictable. Spawning often occurs in groups, especially at reef edges during specific lunar phases. The fish ascend in synchronized bursts into the open water to release gametes. Risky behavior in predator-rich zones, but necessary for the dispersal of eggs. The eggs are left to drift with the currents, part of the vast planktonic soup from which only a few will ever return. Napoleon wrasses are long-lived, with lifespans often exceeding 30 years in the wild, possibly reaching 50. They grow slowly and mature late. Females may take over a decade to reach breeding size. This makes them especially vulnerable to overfishing, particularly for the live reef fish trade, where they are prized as luxury food items. Large adults, especially males, are disproportionately targeted, upsetting the population's delicate reproductive balance. In some areas, they've been wiped out entirely. Their conservation status is currently listed as endangered by the IUCN. In protected zones such as marine reserves, they can still be seen gliding through coral fields, unbothered by divers and cameras. But outside those zones, encounters are increasingly rare. Without protection, the very traits that make them unique, slow growth, specialized diet, territorial behavior, become liabilities. Still, where they persist, Napoleonfish hold a crucial place in the ecosystem. They don't engineer reefs like parrotfish or guard them like triggerfish, but they shape the battlefield with every strategic bite. They are not architects, but enforcers, removing the dangerous, consuming the overabundant, keeping certain pressures in check. Their intelligence is subtle, expressed in learned foraging routes and predator recognition rather than problem-solving feats. Their strength is precise, not reckless. In the choreography of reef life, the Napoleonfish plays neither villain nor hero, but something more complex, a regulator. A creature that does not dominate by speed or stealth, but by a careful application of force and a slow mastery of its surroundings. It does not aim to control the reef. It simply maintains its piece of it, one shattered crab shell at a time. In the quietest corners of the Indo-Pacific seafloor, where coral fragments mix with rubble and fine sand, there lies a shape that barely qualifies as life at first glance. Encrusted in algae, dappled in patchy browns and reds, and covered in wart-like lumps, it appears no different from the stones scattered across the benthic terrain. Small fish hover overhead unaware. Crabs skirt past on cautious legs. Even predators glide inches away without registering the shape as anything but background noise. Yet beneath that hardened disguise rests a creature capable of delivering one of the most potent venoms in the marine world: the stonefish. Sinancea verrucosa, the reef stonefish, is neither fast nor sleek. It does not stalk prey with the elegance of a barracuda or the ambush ferocity of a moray eel. Instead, it specializes in stillness. Total, absolute stillness. This is not a lazy stillness nor a fearful one. It is tactical. Stonefish spend most of their adult lives settled on the seafloor, relying on cryptic camouflage so refined that even experienced divers have mistaken them for lifeless chunks of coral. And that's exactly the point. Movement is risk. Stillness, in the world of a stonefish, is both shield and sword. What the stonefish lacks in mobility, it compensates for in speed, but only in the final moment. It is a lie-in-wait predator, one that snaps into action only when the odds are fully in its favor. When a shrimp or juvenile fish ventures too close, the strike is blindingly fast. A sudden expansion of its buccal cavity creates a pressure vacuum that sucks in the prey in under 0.015 seconds. There are no warning signs, no tension, no visible coil before the spring, just a blur and a gulp. Then the stonefish returns to silence as if nothing happened, jaws settling back into its grim, lumpy frame, blending again with the reef. Yet its predatory skills are not what made the stonefish infamous. It is its defense. Hidden within its dorsal ridge are 13 stout spines, each one connected to a venom gland that operates more like a pressurized delivery system than a simple glandular sac. When threatened, or stepped on, the fish drives those spines upward into the soft flesh of whatever disturbed it. Venom is injected not actively but reflexively, pumped in proportion to the pressure applied. The result is excruciating pain, often described as instant and unbearable, spreading quickly through the limb. For some victims, especially those with compromised health or allergic sensitivities, the venom can be fatal without treatment. For others, the damage includes necrosis, muscle death, and permanent nerve injury. But to understand the stonefish fully, one must examine the evolutionary trade-offs it represents. Unlike other reef predators, the stonefish does not chase or flee. It has sacrificed speed for armor, agility for toxin, and visibility for complete concealment. Its strategy is not to avoid danger, but to punish it, severely enough to deter future encounters. It is the biological equivalent of a landmine, invisible, passive until triggered, and devastatingly effective. This deterrence is so well respected that few marine predators dare to test it. Sharks will investigate stonefish cautiously but rarely bite. Octopuses, clever and nimble, may take the risk if hungry enough, but usually target juveniles or incapacitate them from behind. Even humans, once bitten, develop a powerful aversion to walking barefoot near shallow reefs for life. Despite its fearsome reputation, the stonefish plays a complex role in reef ecosystems. It is not an apex predator, nor is it particularly abundant in most regions. Its value lies in what it controls: populations of small fish and invertebrates that might otherwise overrun delicate benthic zones. It acts as a pressure valve, a quiet regulator of balance, without ever drawing attention to itself. Its existence is a constant low-frequency signal to other organisms. The reef is not as safe as it looks. The stonefish's biology is as strange as its behavior. It possesses a lateral line system, like most fish, to detect vibrations and movement around it. But in its case, this system is tuned for proximity. It doesn't care about far-off swimmers. It wants to know what's within a few centimeters. Its eyes, bulging and upward-facing, help it scan for silhouettes passing overhead. But the eyes themselves are secondary in function to the fish's reliance on pressure waves and chemical signals. In essence, the stonefish perceives the reef through distortion and scent, not clarity. It doesn't need detail. It needs opportunity. During periods of inactivity, which constitute most of its life, the stonefish will allow algae and detritus to settle on its body, enhancing its camouflage. Some individuals look more like rocks than others, depending on the substrate they inhabit. Scientists have observed that individuals may subtly shift location over days, adjusting to better match their surroundings. But these movements are rare and slow, more like adjustments than travel. In captivity, stonefish may remain in the same square meter of space for months, surviving on the occasional meal delivered directly into their gaping mouths. The stonefish's venom is composed of a mix of neurotoxins, cytotoxins, and hemotoxins, making it one of the most chemically complex venoms among fish. One of its main components, verrucotoxin, interferes with calcium channels in nerve cells, leading to the rapid onset of pain and muscle dysfunction. The venom's effects vary depending on dosage, depth of penetration, and location of the sting. In traditional coastal communities, stories abound of fishermen incapacitated for days, and in rare cases, killed after stepping on a buried stonefish. Modern medicine has developed antivenom, but treatment still depends heavily on fast access to care. In remote reef zones, a sting can still be a life-threatening event. Despite all this, the stonefish is not aggressive. It is not a hunter of humans, nor does it patrol the reef looking for confrontation. Its lethality is entirely defensive, a weapon system reserved for the worst-case scenario. Its real strength lies in being ignored, unnoticed, and underestimated, and this may explain why its evolutionary niche has remained so stable. In a world where so many animals rely on mobility, group defense, or visual warning signals, the stonefish operates in reverse. It thrives by disappearing. It survives by becoming the reef itself. There is a certain irony in the fact that such a grotesque and dangerous animal is so often stepped on by accident. The more invisible it becomes, the more likely it is to be disturbed. But this tension is not lost on the fish. When threatened by approach but not touched, stonefish may raise their dorsal spine slightly as a warning posture, though even that is difficult to see unless one knows what to look for. They rarely flee. They don't inflate or flash color. Their warning is embedded in their stillness, their silence. In ecosystems where predators and prey are locked in endless cycles of adaptation, the stonefish represents a kind of equilibrium, not through speed or aggression, but through deterrence and deception. It is not trying to win the game of survival through domination. It's playing not to lose. And in the reef's tight quarters, surrounded by hungry mouths and prying eyes, that might be the smarter strategy. On the list of species most likely to be misunderstood, the stonefish ranks high. To some, it is merely a hazard to avoid, a spiky nuisance lurking where bare feet dare to tread. But to the reef, it is a pressure that keeps prey populations in check and reminds other predators of the cost of careless hunting. Its power is hidden not just in its venom, but in its ability to rewrite the rules of reef warfare. It doesn't chase, it waits. It doesn't warn, it responds, and it never ever blinks. In the southernmost stretches of the world, where sea and sky blur into a white and steel-grey monotony, life clings to the ice with persistence rather than abundance. Winds roar uninterrupted across Antarctic shelves, slicing through exposed rock and snowdrifts with a bitterness that no mammal, bird or human can ignore. Icebergs drift like wandering fortresses, their undersides illuminated in an eerie aquamarine that glows from below. And beneath this surface, under the crushing silence of hundreds of meters of frigid seawater, there is movement that defies the cold, the weight, and the apparent lifelessness. Here, penguins become something else entirely. Not comic, waddling birds on land, but sleek, engineered divers shaped by evolution to thrive in one of the most hostile marine environments on Earth. To see a penguin in its true element, one must follow it off the ice shelf and into the water. As it leaps from the edge, its body tucks into a streamlined torpedo, wings flattened into hydrodynamic flippers that barely resemble those of its flighted cousins. Once submerged, speed replaces awkwardness. Gen 2 penguins, for instance, can reach bursts of 22 miles per hour, rivaling tuna and outpacing most reef fish. Even the slower emperor penguin, the largest species, moves with remarkable control, gliding and banking as if it were an aircraft locked in tight maneuvers. Flippers beat rhythmically, not for lift but for propulsion, pushing the bird forward with a stroke that sends trails of bubbles spiraling behind. Their dives are brief but efficient, often lasting between 2 and 5 minutes for smaller species, though emperors can dive for over 20 minutes and reach depths exceeding 500 meters. In these moments beneath the ice, penguins switch from air-breathing surface dwellers to deep-sea hunters. Their hemoglobin has evolved to bind oxygen more tightly, and their muscles store oxygen-rich myoglobin to extend submersion. They can slow their heart rate and redirect blood flow to vital organs, conserving every molecule of oxygen in a manner more reminiscent of marine mammals than birds. In the frigid shallows, krill clouds shimmer like drifting smoke, broken only when penguins plunge into them in synchronized waves. Hunting is often a group endeavor. Chinstrap and Adelie penguins, for example, coordinate movements in underwater flocks, herding schools of small fish or krill into dense pockets before lunging in from multiple angles. These cooperative behaviors increase the efficiency of feeding, reduce the chance of escape for prey, and provide some measure of defense against lurking predators. Because in these same waters, hovering just beyond visibility, are the dangers that define life under the ice. The leopard seal is among the most formidable of these predators, a top-tier marine hunter with jaws that rival those of large terrestrial carnivores. While it feeds mostly on fish and squid, during the penguin breeding season it becomes a specialist in ambush. It waits at ice edges, near launch points, or underneath breathing holes, relying on the element of surprise. Penguins are acutely aware of the threat, and their behavior changes accordingly. They rarely enter the water alone, often hesitating as a group before committing. Some will dive and surface multiple times, testing the waters for signs of danger. Once in, their speed becomes their shield, but not always. Predation events are fast and violent. A leopard seal will snatch a penguin mid-swim and thrash it violently to tear flesh from bone. Yet even here, penguins display agility that belies their stubby, land-bound form. Some escape through sheer acceleration, twisting mid-dive and darting through narrow gaps in the ice, or even launching themselves from the water in a behavior called porpoising, repeated leaping that allows breathing without slowing down and makes it harder for predators to predict their path. While the external pressures are dramatic, internal survival is no less complex. Emperor penguins must dive through ice-crusted seas in the pitch darkness of Antarctic winter, when sunlight never touches the surface. These dives are not casual. They are necessary for survival and chick provisioning. With no access to land-based food sources, they must find fish and squid in a black, freezing abyss, relying on spatial memory, pressure gradients, and possibly geomagnetic cues to navigate. It is a feat no other bird attempts to this degree, and few mammals match in consistency. Above water, the penguin's life is paradoxical. It is built for cold, but must manage the thin line between hypothermia and overheating. Their feathers are tightly packed, over 100 feathers per square inch in some species, creating a waterproof barrier that traps warm air. Beneath this, A thick layer of blubber insulates the core. Yet on land, under direct sun, especially during the Antarctic summer, overheating becomes a risk. Penguins manage this by holding their flippers out to radiate heat, panting, and seeking shade near rock faces or ice overhangs. It's a delicate physiological balance, keeping enough warmth to survive the water, but shedding enough to avoid collapse on land. Their nesting colonies are loud, chaotic affairs. Emperor penguins form massive huddles in the coldest months, rotating positions so individuals spend equal time in the wind-blasted periphery and the warmer core. Gentoo and Adelie penguins nest on ice-free rock, using pebbles to construct simple nests that become sources of both pride and competition. Theft is common, so is display. Males show off pebbles or call with strange guttural sounds, reinforcing bonds and attracting mates. These terrestrial scenes often create the mistaken impression that penguins are clumsy and endearing, which they are, but only half the time. In the water, there's something else entirely. Efficient, ruthless, and extraordinarily well adapted. One of the most surprising aspects of penguin physiology is how they maintain buoyancy and energy in such demanding environments. Unlike most birds, their bones are not fully hollow. Slightly denser skeletons reduce buoyancy and make diving more efficient. Their fat reserves, while crucial for warmth, are carefully regulated to avoid excessive flotation. Their circulatory systems, including counter-current heat exchange in the flippers and legs, help prevent heat loss without freezing extremities. All of this allows them to spend hours each day in waters that hover just above freezing without becoming sluggish or vulnerable. Species vary by range and behavior. Emperor and Adelie penguins are true Antarctic residents, while others, like Magellanic, Humboldt, and African penguins, occupy temperate zones. Even the Galapagos penguin, living near the equator, must cope with cold water due to upwelling currents. Each species brings different strategies to the same aquatic challenge. Some dive shallow and often, others deep and sparsely. Some nest in burrows, others on open rock. But all share a dependence on the sea for food, and a body that has been sculpted more by ocean than air. There is irony in their evolutionary trajectory. What began as a lineage of flying seabirds eventually abandoned the sky entirely. Wings became flippers. Lift gave way to thrust. Their ancestors sacrificed the open air for denser, colder, more alien depths, and thrived. In doing so, penguins became some of the most specialized avian divers alive, capable of navigating a medium that most birds avoid entirely. In underwater warfare, the penguin's strategy is not brute strength or toxin. It is speed, cohesion, and intelligence. They use group tactics, fluid dynamics, and escape maneuvers honed by millions of years of predation pressure. They are not predators of large prey, but neither are they passive grazers. In a marine world dominated by the fanged and finned, penguins are anomalies, warm-blooded, feathered, and flightless, yet among the most successful aquatic hunters on Earth. On land, they remain bound to cycles of breeding and molting, their vulnerability exposed in every clumsy step. But beneath the waves, they become what the wind and ice cannot touch. Steel divers, torpedoes in feathered disguise, slipping silently through the dark beneath the frozen ceiling of the Southern Ocean. Off the jagged, wind-beaten coastlines of the North Pacific, stretching from the Kuril Islands to the Alaskan archipelagos and down through British Columbia and California, a forest floats. Its trees are not rooted in soil, but anchored to seafloor rock by holdfasts, rising to the surface in long green ribbons. Kelp forests, dynamic, swaying, sun-filtering jungles that reach from the dark benthos to the churning, light-dappled surface. Within these vertical ecosystems of fronds and shadows, a predator moves not with speed, but with precision and intelligence. The sea otter. To watch a sea otter in motion is to observe a blend of buoyancy and calculation. Unlike sleek orcas or bullet-shaped tuna, the otter does not slice through the water with high-speed efficiency. Instead, it drifts and maneuvers with fine-tuned control, using webbed hind feet like paddles and a rudder-like tail for gentle steering. On the surface, it lies on its back, belly up to the sky, appearing more relaxed than any other marine hunter. But beneath this seemingly casual posture is a highly developed set of behaviors, tool use, and foraging strategies that place the sea otter among the most intelligent predators in the ocean. The sea otter is small compared to the giants of the Pacific, rarely exceeding 45 kilograms in weight. yet it possesses the densest fur in the entire animal kingdom, up to 1 million hairs per square inch. This is not a luxury, but a necessity. Unlike seals or whales, the sea otter lacks a thick layer of insulating blubber. Instead, it relies entirely on its fur and the air trapped within it for thermal protection against waters that rarely rise above 5 degrees Celsius. This dependence forces the otter into constant grooming, combing and fluffing its fur with forepaws to maintain the insulating air layer. Should its fur become soaked or matted, hypothermia becomes a real and rapid threat. It is a predator that must balance the demands of feeding with the maintenance of its own survival system, one that requires nearly obsessive attention. Beneath the kelp canopy, the otter forages with purpose. It does not chase its prey over distance. It dives down, often to depths of 10 to 40 meters, seeking out invertebrates that few other predators can efficiently access. Crabs, mussels, clams, sea urchins, abalone, each protected by hardened shells or defensive spines, form the otter's primary diet. To breach these defenses, the otter employs a toolkit as sophisticated as anything found in the animal world. Holding a stone or similar hard object on its belly, the otter smashes prey against it, breaking open shells with rapid, practiced motions. This use of external tools, combined with a unique loose skin pouch under each forearm to store both tools and food, has placed the sea otter at the forefront of non-human animal intelligence studies. Every foraging dive is a tactical operation. The otter uses its nimble front paws to root around in crevices, feeling for movement and texture. Sea urchins are collected carefully to avoid injury from the venom-tipped spines. Clams are pried from the substrate and brought to the surface.
On its back, the otter begins the work. Stone in paw, shell on belly. A few rapid strikes, a twist, a crack.
Then the soft tissue is extracted and consumed, often with eyes closed, as though savoring the reward. In a single day, an adult sea otter may consume 25 to 30% of its own body weight in food. This voracious appetite is not indulgent, it's essential. Maintaining body heat in cold water without blubber requires constant caloric intake. Without sufficient food, the otter starves not slowly, but swiftly. What makes the sea otter's ecological role so striking is not just what it eats, but how its presence reshapes entire ecosystems. In areas where otters are abundant, sea urchin populations are kept in check. This allows kelp forests to thrive, as unchecked urchins can devastate kelp beds by grazing down their holdfasts and reducing entire forests to underwater deserts. Where otters are removed, urchin barrens form, wastelands of bare rock and short algae stubble. With otters, the kelp returns, and with it, a cascading web of biodiversity, including fish nurseries, invertebrate abundance, and carbon sequestration. In this way, the sea otter is a keystone predator, not just surviving within an ecosystem, but actively engineering it. Yet this power comes with vulnerability. Sea otters were nearly eradicated by the fur trade in the 18th and 19th centuries. Their dense pelts, coveted for warmth and luxury, drove them to the brink of extinction across much of their range. By the early 1900s, only a handful of remnant populations survived. Recovery efforts, legal protection, reintroduction, and marine conservation have allowed numbers to rebound in some regions. But challenges persist. Oil spills, such as the Exxon Valdez disaster, proved devastating for otters, as oil compromises their fur's insulating properties. Additionally, some fisheries view sea otters as competitors, particularly for shellfish, leading to tension and illegal culling. In Alaska and parts of Russia, changes in orca diets, possibly related to broader marine food web disruptions, have also resulted in increased predation on sea otters, altering local population dynamics. The life of an otter is not only about feeding and survival. Reproduction and social behavior add further complexity. Females raise pups alone, often carrying them on their bellies for weeks until the young can swim and dive independently. During this time, the mother must continue to feed herself while protecting the pup from cold and predators. In extreme conditions, she may wrap the pup in kelp to prevent it from drifting while she dives for food. Pups are born with thick natal fur that is so buoyant they cannot dive, a helpful trait early on, but one that makes them entirely dependent on the mother. This parental investment is among the highest in the marine world for a carnivore of its size. Socially, sea otters form loose aggregations called rafts, sometimes numbering in the dozens. Males and females often segregate into different rafts outside of breeding season. Within these groups, behaviors range from cooperative grooming to aggressive displays, especially during mating. These interactions reveal a species that is not solitary, nor truly gregarious, but rather socially flexible, capable of adapting its behavior to conditions, resources, and reproductive needs. The sea otter's intelligence extends beyond tool use. Observational learning has been documented in both wild and captive populations. Individuals can learn new foraging techniques by watching others. Some populations specialize in particular prey based on local availability, developing what amount to cultural foraging traditions. In a marine world where most predators rely on speed, size, or sensory extremities, the otter's strategy is cognition. Its weapons are not sharp teeth or venomous spines, but memory, manipulation, and patience. In the swaying underwater canopy of the kelp forest, the otter is both hunter and sentinel. Its movements are careful, deliberate, and precise. It patrols not with dominance but with persistence, enforcing balance not by terror but by habit. Unlike many ocean predators that operate in bursts, short chases, sudden strikes, explosive ambushes, the otter is engaged in a war of attrition. Every dive, every cracked shell, every pawful of prey is part of a broader strategy. Stay warm, stay fed, stay hidden. And in doing so, the otter reshapes the environment to its advantage, maintaining a forest where few others could, and holding the line against the slow creep of ecological collapse. In the end, the sea otter is a contradiction in motion. Small, yet powerful. Vulnerable, yet influential. Cute by appearance, but ruthless in purpose. It floats lazily, but lives furiously, balancing the demands of cold survival with the maintenance of an entire ecosystem. It does not conquer the sea with force, but with strategy. An ice sentinel patrolling not with teeth, but with tools, along the fractured edge of the Arctic Circle, where slabs of sea ice grind against one another in slow-motion collisions, and the wind never ceases its low, frozen moan. A different kind of army assembles. From a distance, they appear as motionless shapes strewn across a floe. Brownish-grey mounds arranged in irregular clusters, like driftwood stranded by retreating tides. But as the ice shifts and the cold air thickens with sound, the shapes stir. Grunts rise in chorus. Heads lift, revealing whiskered snouts and narrow eyes. The frozen silence breaks under the guttural bellow of a male walrus claiming space, and the tension that lies beneath their placid surface begins to show. Odobenus rosmarus, the walrus, is not the fastest nor the most agile of Arctic predators, but it is among the most physically formidable. An adult male can weigh over 1,500 kilograms, its weight supported by a barrel-shaped body wrapped in thick layers of blubber that serve as both energy reserve and insulation. The skin, wrinkled and leather-like, can measure up to 4 centimeters in thickness, natural armor against bites, cold, and abrasion from ice. Along its upper jaw protrude a pair of tusks, 1 to 1.5 meters in length, used for dominance displays, combat, and anchoring on the ice. These ivory weapons are not just for show. They are integral to the walrus's social structure and survival. The walrus's realm spans the shallow continental shelves and marginal ice zones of the Arctic Ocean, where it feeds not by stalking, but by sifting. An enormous bulk refined into a specialized benthic predator. Dropping from the ice into turbid water, it begins to transform. Using its powerful front flippers, the walrus propels itself downward to the seafloor, where visibility diminishes to inches. Here, in the murk, the walrus forages with a precision that belies its size. Its sensitive vibrissae, whiskers packed with thousands of nerve endings, sweep across the sediment, detecting the faintest movement or contour of buried prey. The target is most often bivalves, clams, cockles, and other mollusks that lie hidden just beneath the surface. With a powerful suction force created by retracting its tongue, the walrus can extract soft flesh from shells without using its teeth at all. Crushed shell fragments and sand are often spit out after the fact, leaving behind feeding craters that pockmark the Arctic seabed. Despite their intimidating appearance, walruses are rarely aggressive toward other species unless provoked. Their social structure revolves around large aggregations, hundreds, sometimes thousands of individuals gathered on ice floes or beaches. These herds are noisy and chaotic, with constant vocalizations ranging from deep rumbles to trumpet-like blasts that help maintain individual spacing, signal stress, or communicate readiness to mate. Within these gatherings, hierarchy is clear. Older males often command prime positions, and disputes over space or mates can erupt into displays of dominance, sometimes escalating into tusk-on-tusk clashes that leave scars or fractured ivory behind. But most contests are ritualistic. Posturing, loud calls, and mock charges designed to avoid unnecessary injury in a world where wounds can become fatal liabilities. The sheer density of these colonies also plays a defensive role. Walruses may not be nimble, but they are powerful in numbers. When danger appears, be it a polar bear on the ice or an orca patrolling nearby waters, the herd reacts as a unit. Mothers press calves between their flippers. Adults form loose phalanxes around the vulnerable. In water, their mobility increases dramatically. Despite their bulk, walruses can swim for extended periods and dive over 90 meters when needed. But it is on land and ice that their coordination becomes most evident. Polar bears, though fearsome, rarely target full-grown walruses. Their preferred targets are isolated calves or weakened adults. Even then, a charging walrus can turn the tide, using tusks to gore or shove, turning a hunt into retreat. Orcas, more effective in the sea, have been observed isolating individual walruses, especially young or old ones, but attacks often end in retreat unless the walrus is already compromised. The success rate of such predations is far lower than popular narratives suggest. Walruses are migratory, their movements dictated by the seasonal dance of sea ice. In summer, as the ice recedes, they follow its edge northward, clinging to platforms that allow access to productive feeding grounds while offering a base for resting and protection. In winter, they may haul out on land when ice becomes scarce, especially in the Bering and Chukchi seas. Climate change, however, is altering this rhythm. With sea ice forming later and retreating earlier, walruses are increasingly forced to haul out on land in enormous numbers, sometimes in areas where space is limited. This has led to deadly stampedes, particularly when herds are startled, an event that can crush calves and cause severe injuries. The frequency of such incidents is rising, underscoring the fragile balance between environment and survival. The walrus's reproductive strategy adds another layer to its ecological complexity. Mating occurs in the water, often in late winter or early spring, with males vocalizing underwater in elaborate displays to attract females. These sounds, including bell-like pulses and knocks, are produced using specialized air sacs in the throat and resonate across long distances. Once impregnated, the female carries the embryo in a state of delayed implantation, ensuring that birth coincides with optimal conditions the following year. Calves are born on the ice and nurse for over a year, during which they learn not just to feed and swim, but to navigate the social cues and dangers of the herd. Walrus calves are precocious swimmers, able to follow their mothers on dives within weeks of birth. But they remain closely bonded to their mothers for up to 2 years, and in many cases, longer associations persist. The maternal investment is high, and mortality among calves, due to predation, separation, or accidental trampling, is not uncommon. Mothers are fiercely protective, placing themselves between danger and their young, vocalizing to maintain contact, and physically lifting or dragging calves when necessary. The degree of parental care in walruses rivals that seen in elephants or primates, reinforcing their reputation not just as massive marine mammals, but as complex, social animals. The Arctic is often perceived as a stark and lifeless expanse, but in the presence of a walrus colony, it becomes something else, a living, breathing arena of biology and behavior. The scent of salt, fish, and mammal oil hangs heavy in the air. The noise is relentless, a chorus of snorts, grunts, and splashes that echo off nearby cliffs or ice. The visual field is a landscape of motion. Bodies shifting, tusks gleaming, calves nursing, males posturing, all within a world that seems otherwise devoid of life. And yet this fragile scene is now more imperiled than ever before. As sea ice declines, the walrus faces not just spatial challenges, but energetic ones. Longer swims to feeding grounds mean higher caloric demands, and in turn, more time foraging. Increased time in the water also exposes calves to greater risk from predators and exhaustion. The resilience of the walrus is undeniable. These animals have weathered glacial cycles, ice ages, and the rise and fall of empires. But the pace and scope of modern climate disruption pose novel threats. The same tusks that have held firm against orcas and bears offer no defense against vanishing ice. Yet the walrus remains a sentinel of the North, not just symbolically, but functionally. Its presence signals the health of the marginal seas, the abundance of benthic life, and the stability of Arctic systems. To watch it haul out, to hear its voice resonate across the frozen shore, is to witness more than an animal. It is to glimpse the architecture of a marine world that relies on ice not just as habitat, but as scaffolding for life. In this way, the walrus does not patrol the Arctic like a conqueror, but like a guard, immense, deliberate, and bound to the changing rhythms of a frozen frontier.
And as long as the ice holds, so does the balance. The shallow reef appears tranquil at first glance.
Sunlight filters through the turquoise water, scattering light across ridges of coral and sending gentle ripples across the sandy seabed. Fish pass overhead in steady rhythms, darting, cruising, pausing to nibble at algae or inspect the movement of others. Everything seems in motion except for one organism, swaying gently among the reef's nooks, like a slow-motion bloom in a current that never rests.
Its colorful tentacles, arrayed in soft radial symmetry, dance like petals in the underwater breeze. But this is no passive plant. It is one of the reef's most deceptive killers, the sea anemone.
Actiniaria, the order encompassing sea anemones, includes over 1,000 known species, each adapted to a slightly different ecological niche. Some live tucked deep within rock crevices, others sprawl across coral heads, and a few even drift with currents as free-swimming larvae before settling into a life of anchored stillness. But what they share universally is a method of predation that defies their immobility. They don't chase prey, they don't stalk. They wait, tentacles outstretched, and let life come to them. When it does, they strike with microscopic precision and biochemical force. Each tentacle is equipped with hundreds to thousands of specialized stinging cells, called cnidocytes. Inside each cnidocyte lies a harpoon-like organelle called a nematocyst. When triggered by touch or chemical cues, the nematocyst explodes outward, injecting venom into the prey within a fraction of a second. The effect is paralyzing. A small fish brushing against the anemone may initially twitch, then freeze as neuromuscular control collapses. Cilia on the anemone's surface then guide the limp body toward the central mouth. Digestion begins externally as enzymes break down tissue before the meal is fully ingested. All of this occurs without chase, without noise, without drama, just an invisible strike in a field of color. But the sea anemone does not only rely on toxic stings. Its effectiveness as a predator is amplified by an unexpected alliance, a symbiotic relationship with certain species of fish, most famously the clownfish. In the Indo-Pacific reefs, these orange and white striped fish weave through the anemone's tentacles as though immune to its sting, which, remarkably, they are. Coated in a mucus that mimics the anemone's own chemical signature, clownfish are accepted as part of the anemone's self and are allowed to live safely within its venomous grasp. For the clownfish, the protection is obvious. Few predators dare approach the toxic tangle of tentacles, but the benefit for the anemone is more subtle and no less significant. Clownfish actively defend their host anemone, chasing away butterfly fish and other would-be nibblers that prey on tentacle tips. They also stir the water as they move, increasing oxygenation around the anemone's base. And their waste provides essential nutrients, enriching the surrounding environment in a system where nutrient scarcity often limits growth. In return, the anemone provides the clownfish with a fortified fortress, a mobile lookout stationed in the heart of a biological trap. This partnership blurs the line between ambush predator and ecosystem microengineer. When a predatory fish comes too close, curious about the clownfish or seeking smaller prey, the anemone gains a rare opportunity. The clownfish may dart outward as bait, triggering a chase that ends in a sudden fatal brush against tentacles. In this way, the anemone doesn't just sit and wait. It leverages alliance and behavior to create opportunity. Not all sea anemones rely on partnerships. Some species have evolved entirely different feeding adaptations. Tube anemones, for instance, burrow into the sediment and remain almost entirely hidden, sending only a crown of tentacles above the surface. Others exhibit striking mobility, capable of inching across the substrate when necessary. Though slow, this locomotion allows them to reposition based on competition, light availability, or threat. It also debunks the common misconception that all anemones are static. They are slow, but not inert. Their reproductive strategies are equally varied. Sea anemones can reproduce both sexually and asexually. In some species, individuals release gametes into the water column, relying on external fertilization and drifting larvae to find suitable substrate. In others, especially those in colder or more isolated environments, budding or fission is common. A single anemone can split into two, producing genetically identical clones. Entire colonies can form this way, dense mats of genetically uniform individuals that blanket rock surfaces like toxic carpets. Some tropical reefs are home to vast aggregations of clone armies, all born from one original anemone that fragmented and multiplied over time. This reproductive plasticity serves an evolutionary purpose. In high predation zones or where space is limited, cloning allows anemones to defend territory efficiently and occupy ecological real estate without the randomness of larval dispersal. But it also creates competitive pressure among clones. When two colonies of different genetic lines meet, they may engage in a slow-motion battle of attrition, extending specialized fighting tentacles equipped with extra venom to sting and kill competing tissue. The border between anemone colonies, therefore, is not always peaceful. It is a toxic trench war measured in millimeters per month. The venom of sea anemones is complex and still not fully understood. Some species produce toxins that target nervous systems, while others focus on cell membranes causing rupture and necrosis. Researchers have found bioactive compounds in anemone venom that show promise in medical research, including pain blockers more potent than morphine and proteins that inhibit cancer cell proliferation. Their biochemical arsenal is a product of evolutionary pressure to kill quickly and defend territory. To the casual swimmer or diver, the anemone may look like an undersea flower, but to the organisms that live and die in its presence, it is a weapon system, one that has remained unchanged for millions of years because it works. Sea anemones also have an indirect but profound influence on reef dynamics. By occupying space and filtering water, they help control sedimentation and local nutrient flow. Their presence creates microhabitats for smaller organisms, shrimp, crabs, gobies, that live beneath or between tentacles, each with their own adaptations to avoid triggering the sting. These residents, in turn, attract predators or scavengers, forming miniature ecosystems anchored to a single organism. In areas where coral dies off due to bleaching or disease, sea anemones may even take over as dominant space holders, creating new reef landscapes with their own ecological rules. And yet, despite their defenses, sea anemones are not immune to threat. Rising ocean temperatures, acidification, and pollution can disrupt their symbiotic relationships. Without healthy zooxanthellae, algae that live inside their tissues and provide energy through photosynthesis, many anemones bleach, lose color, and die, much like their coral cousins. Additionally, certain species of starfish, nudibranchs, and even fish have evolved ways to feed on them, braving or bypassing the sting through thick mucus coatings, speed, or careful biting strategies. In nature, no defense is absolute. To watch a sea anemone feed is to witness a paradox. A creature that cannot chase or flee still manages to dominate a section of the reef with lethal elegance. It represents a model of predation that relies not on speed or size, but on patience, chemistry, and design. It is a fixed turret in a battlefield of motion, one that compensates for immobility with one of the fastest and most precise biological strikes on the planet. The sea anemone thrives in the stillness. It waits, it watches through its chemical senses. And when something ventures too close, lulled by color or distracted by the clownfish dancing above, it reacts with a violence that is invisible to the naked eye. No teeth, no jaws. Just contact, sting, paralysis, and silence. In the war beneath the waves, the flower assassin remains motionless, but never harmless. Far below the surface, beyond the reach of light, where pressure crushes like a hydraulic vice and temperatures hover just above freezing, the world turns silent, at least to human ears. At these depths, hundreds of meters beneath the open ocean, the visual world collapses into darkness. Eyes become irrelevant. Speed gives way to endurance. Here, survival depends on adaptation not of form but of perception. And in this blackened water column, a colossal predator swims slowly, deliberate and calm, relying not on sight or smell, but on sound. Pulsing, clicking, echoing sound, controlled, calculated, and at times weaponized. This is the realm of the sperm whale. Physeter macrocephalus is the largest toothed predator on Earth. Males can reach up to 20 meters in length and weigh over 50 tons, their massive heads comprising nearly a third of their total body length. The anatomy of this head is no accident. Inside lies the most sophisticated acoustic weapon system nature has ever developed. The spermaceti organ, named after the waxy substance it holds, fills much of the upper skull and plays a critical role in sound production and focusing. Just beneath it lies the monkey lips, an oddly named pair of air-filled passages where sound clicks are generated. These clicks are then channeled through the spermaceti organ, focused like a beam, and projected into the depths at volumes that can exceed 230 decibels, louder than a shotgun blast and potentially louder than a jet engine at takeoff. But these sounds aren't just loud, they're structured. Sperm whales use patterns of clicks not only to communicate, but to perceive the world around them through echolocation. Every click sent into the void returns a signature bounce, a squid's rubbery outline, the echo of a canyon wall, the shadow of a distant school of fish. The whales interpret this returning data in a kind of auditory vision, constructing mental maps of terrain and prey in an environment where eyes are useless. Their brains, the largest of any animal on Earth, process these echoes with incredible efficiency. It is, in effect, a high-frequency scanning system honed by evolutionary necessity. When a sperm whale dives, it enters a different physical and biological reality. Starting with a series of shallow breaths at the surface to hyperoxygenate its blood, the whale then draws a final breath and arches downward, vanishing into the blue. As it descends, its heart rate slows dramatically, sometimes to just 3 or 4 beats per minute, to conserve oxygen. Blood flow is restricted to vital organs. Lungs collapse under the pressure, reducing buoyancy and preventing nitrogen absorption that could lead to decompression sickness. The whale does not panic. It glides, descending at a steady rate of 1 to 2 meters per second, sometimes diving over 1,000 meters and staying submerged for over an hour. At these depths, prey is sparse but formidable. Giant and colossal squid, the elusive behemoths of the deep, make up a significant portion of the sperm whale's diet. These squid are not passive targets. Some possess suckers lined with chitinous teeth, capable of latching onto flesh and leaving circular scars. Scars commonly seen on the heads and bodies of mature sperm whales. The hunts are not brief ambushes, so not. They are prolonged chases in darkness, sensory battles where each participant is equipped for the abyss. But the whale has a secret advantage: its sonar. Researchers believe that sperm whales may use intense clicks not only to detect prey, but also to disorient it. Some of the strongest clicks are emitted just before a strike, and while not conclusively proven, the prevailing theory suggests these clicks can overload a squid's sensory systems, causing temporary paralysis or confusion. At such close range, the sound is not just information, it becomes force. In this way, the whale doesn't just use echolocation to find prey. It may weaponize sound to disable it. The final moments of a hunt are nearly impossible to observe. Human technology cannot keep pace with a whale at depth, and no camera has yet captured a full hunt in real time. But indirect data, biologging tags, stomach contents, acoustic records, paint a consistent picture. After a flurry of clicks and a sudden acceleration, the whale seizes its prey with a lower jaw lined with up to 50 large conical teeth. It does not chew. Squid are swallowed whole or torn into large chunks using suction and jaw pressure. Then, the whale begins its slow return to the surface. Lungs still collapsed, heart still slowed, body temperature maintained by thick blubber and thermal inertia. At the surface, sperm whales often spend several minutes breathing, reoxygenating blood, releasing carbon dioxide, and preparing for the next dive. These breathing intervals are marked by a distinct blow, angled forward due to the off-center position of their single nostril, and a rhythmic series of exhalations that hint at the effort just expended below. Often, social behaviors resume during these periods. Female sperm whales and calves form close-knit groups called matrilineal pods, usually composed of related individuals. These groups are highly stable and may last for decades. Adult males, on the other hand, are largely solitary or form loose bachelor groups, only joining female pods for breeding. Within these pods, communication becomes layered and complex. Coda, short patterns of clicks, are exchanged between individuals in sequences that resemble dialects. Different populations across oceans display distinct coda repertoires, suggesting a kind of cultural evolution in acoustic signaling. These codas are not used for echolocation, but for social bonding and identity, a second acoustic language layered on top of their already sophisticated sonar. It's as if the sperm whale operates with two sound systems, one for perceiving the world, another for navigating society. Sperm whales do not dominate the ocean through aggression, but through persistence. Their hunting success relies on repetition rather than efficiency. They dive, feed, and surface in cycles that consume most of their waking hours. In any 24-hour period, a sperm whale may spend up to 70% of its time submerged in near-complete darkness, far from visual stimuli, relying on sonar and memory to survive. Their range is vast, from equatorial waters to the edges of polar seas, migrating in response to prey movement and breeding demands. And despite their size, they remain vulnerable, targeted historically by whaling ships for the valuable spermaceti oil in their heads. These hunts decimated populations, particularly in the 19th and early 20th centuries. Even today, collisions with ships, entanglement in fishing gear, and the accumulation of pollutants pose serious threats. And yet, the sperm whale endures, not by adapting to surface threats, but by doubling down on the deep. It remains one of the few animals capable of operating routinely in the midnight zone of the ocean, a place of crushing pressure, total darkness, and elusive prey. Few species can challenge its reign there. Sharks don't dive so deep. Dolphins prefer shallower prey, and even orcas tend to hunt in higher layers of the sea. In the soundless dark where light fails and pressure rules, the sperm whale dominates through biology sharpened by time. From the outside, a sperm whale's bulk suggests slow simplicity. But internally, neurologically, acoustically, behaviorally, it is one of the most advanced marine hunters alive. It doesn't rely on speed or stealth. It doesn't ambush like a crocodile or swarm like a wolf pack. Instead, it scans, calculates, and stuns, moving with a confidence that only a perfectly tuned predator of the deep can exhibit. It hears what others cannot. It sees with echoes. It kills with sound. In the vast underwater battlefield, where vision fades and touch is rarely an option, the sperm whale thrives not through force, but through focus. It has turned the ocean into an acoustic landscape and reshaped the act of hunting into a neurological performance. In the silence of the deep, it is not the roar of a predator that signals danger, but the click. Relentless, rhythmic, and devastating. At the edge of a sunlit seagrass bed, where sand drifts softly over silt and blades sway in gentle tidal motion, a tiny figure holds perfectly still. Its posture seems awkward by conventional fish standards, upright, rigid, and motionless. But this is not a fish designed for speed or strength. This is a seahorse, a master of subtlety. Suspended among the stems of eelgrass or anchored to coral rubble by a prehensile tail, it appears as much a part of the vegetation as any drifting leaf. Even with careful observation, it's easy to miss, camouflaged not just by color, but by posture and stillness. But make no mistake, for the amphipods, copepods, and larvae drifting by, this motionless creature is a predator, one finely tuned for ambush in miniature. Seahorses belong to the genus Hippocampus, a group of around 45 known species that inhabit temperate and tropical waters across the globe, from mangrove estuaries to coral reefs to sheltered bays. Despite their delicate appearance, they are specialized hunters, adapted to a hunting style that favors patience and precision over pursuit. They lack teeth and stomachs, two traits that would seem crucial to a predator. But evolution has granted them something else entirely: a weaponized snout and a technique that defies their size. To understand the seahorse's hunting strategy, you must slow down the action to a frame-by-frame level. When prey, a tiny shrimp or zooplankton, drifts within a few millimeters of its snout, the seahorse snaps forward with astonishing speed. Its head pivots upward on a fixed joint, and a powerful suction is created in its long, narrow snout, drawing the prey inward in less than a millisecond. The action is so fast that even high-speed cameras struggle to capture it in full detail. The process is called pivot feeding, and it relies on elastic energy stored in tendons near the back of the head. When released, the resulting vacuum is strong enough to overcome the inertia of even fast-moving prey. There is no chewing, no tearing, just disappearance. One moment the prey drifts, the next it's gone, vanished into the vertical predator with a flash of movement and a barely audible pop. Despite their slow swimming speeds and lack of traditional fins, no caudal fin and small, rapidly fluttering dorsal and pectoral fins, their hunting success is remarkably high. This is due in part to their stealth. Seahorses can approach prey without creating detectable water disturbance, a feat made possible by the unique shape of their head and snout. Research has shown that their angular, narrow profile allows them to get close to prey without triggering escape reflexes common in small crustaceans. This makes them some of the most efficient ambush predators on a per-capture basis in the marine world, perhaps not as dramatic as a shark's charge, but far more surgical. Seahorses also possess another trait that places them in rare company, a form of pregnancy reversal. It is the male who becomes pregnant, an adaptation seen nowhere else in vertebrate biology. During mating, the female deposits her eggs into the male's brood pouch, an enclosed, vascularized chamber on his abdomen. Over the following days or weeks, depending on the species and environmental conditions, the male fertilizes and nourishes the developing embryos internally. Oxygen, nutrients, and waste are exchanged via capillary networks that function much like a placenta. When the gestation period ends, the male goes into labor, literally, expelling dozens or hundreds of fully formed miniature seahorses into the open water with spasmodic contractions. The courtship that leads to this unusual role reversal is surprisingly elaborate. Seahorses engage in synchronized dances that can last for hours or even days. Partners mirror each other's movements, curl their tails together, rise through the water column in unison, and change colors as they display physiological readiness. These rituals serve not only to ensure reproductive timing, but also to reinforce pair bonds in species that are often monogamous over the course of a breeding season, or even longer. In the cluttered underwater environment, where visual and chemical signals can be difficult to detect or interpret, such repeated and precise displays help ensure reproductive success. But these gentle-looking dances conceal an undercurrent of territoriality, especially among males. In many species, male seahorses maintain and defend small territories, especially when resources like food and suitable anchor points are limited. Conflicts between rival males, while rarely resulting in injury, involve circling, posturing, and attempts to physically dislodge one another from prime feeding spots. Their tails, often seen wrapped around vegetation or coral, can just as easily be used in tug-of-war style matches against encroaching males. These contests rarely escalate into full combat, but the outcomes determine access not only to prey-rich hunting zones, but also to potential mates. In seahorse society, size matters. Larger males are more likely to win territories and attract females. Yet even smaller males have strategies. Some may avoid direct confrontation by adopting nomadic habits, moving between territories, and seizing mating opportunities when resident males are distracted or absent. Their anatomical oddities don't end there. Seahorses lack ribs, and their bodies are encased in bony plates arranged in rings along the torso and tail. This gives them a rigid appearance, and they swim upright, another rare trait among fish. Their swimming is powered primarily by rapid beats of a small dorsal fin, with tiny pectoral fins steering and stabilizing. They are not built for distance or speed, and even moderate currents can displace them. This is why seahorses are often found in calm, sheltered habitats, where holdfasts, such as seagrass, gorgonians, or mangrove roots, are plentiful. Their tails, flexible and muscular, serve not only as anchors, but as means of locomotion and manipulation. Juveniles, born into open water and without anchorage, must survive their planktonic phase in the drift before settling into suitable habitat. Mortality at this stage is high. An estimated 1 in 1,000 may reach maturity. Camouflage is vital. Many seahorses can change color to match their environment, blending into algae-covered rocks or coral fans. Some species grow filamentous skin extensions that enhance their disguise, resembling the weeds and grasses they inhabit. This camouflage serves a dual purpose. It hides them from predators, and it hides them from prey. Ironically, despite being poor swimmers and defenseless against larger hunters, their best defense is to not be noticed at all. When predators do approach, their primary response is to freeze, relying on their disguise to fool even sharp-eyed hunters. When that fails, their lack of spines, toxins, or speed leaves them vulnerable. This vulnerability has made seahorses a focus of conservation concern. They are harvested for use in traditional medicines, aquarium trades, and as dried curios in various cultures. Millions are taken annually, often as bycatch in bottom trawling nets. Their small ranges, low reproductive rates, and specialized habitat needs make them particularly sensitive to disturbance. And yet, in many regions, they remain understudied, their populations difficult to monitor due to their elusive nature. Protecting seahorses often means protecting the ecosystems they inhabit, seagrass meadows, mangrove forests, coral rubble flats that support countless other species. To observe a seahorse in its environment is to witness a contradiction made functional. It is fragile, yet predatory, slow, yet efficient, limited in range, yet precise in its execution of life's essential tasks. Its strategy is one of deliberate restraint, a life lived quietly among the blades and fronds, hunting without chase, courting without conquest, defending without destruction. The seahorse has no fangs, no claws, no toxins, and no speed. But it doesn't need them. It survives by removing all unnecessary motion from its existence. It thrives through timing, adaptation, and a surprising tactical edge in its niche. And in the small world it claims, just a few square meters of grass or reef, it rules not through dominance, but through quiet precision. In a sea full of giants and monsters, the seahorse wins by simply being still, sharp, and ready. Beneath the sunlit shallows and into the dimmer margins of the continental shelf, the ocean floor becomes a quiet, grainy expanse. Here, the coral architecture begins to thin out, giving way to soft sediments, scattered shells, and the slow crawl of benthic life. Few movements break the stillness. Fish skim across the bottom, rays sift through the sand, and among them lies a shape that appears entirely inert, a mottled tube stretched across the seabed like a discarded sleeve. There are no visible eyes, no expression, no intent. But the creature is very much alive. This is a sea cucumber, one of the least appreciated yet most essential organisms shaping the battlefield from the bottom up. Sea cucumbers belong to the class Holothuridae, and though they bear little resemblance to their starfish and sea urchin relatives, they share the same echinoderm heritage. Their bodies are soft and gelatinous, often cylindrical, and range in size from just a few centimeters to over 2 meters in length, depending on the species. Unlike the dramatic hunters of the sea, sharks, cephalopods, and marine mammals, sea cucumbers do not pursue, ambush, or overpower their targets. They are slow, methodical detritivores that feed on organic matter settled in the sediment, earning them the unflattering but accurate title of ocean janitors. Yet their contribution to marine ecosystems is not just passive, it is transformative. To witness a sea cucumber at work is to see a continuous loop of ingestion and filtration. Using tentacle-like oral structures that radiate from the mouth, often tucked under the body, the animal gathers sand, mud, and detritus. This mixture is drawn into the digestive tract, where organic particles, bits of decaying algae, plankton, fish waste, are separated and absorbed. The remaining clean sediment is expelled out the other end, sometimes forming long, neat coils behind the moving animal. Over the course of a single day, a medium-sized sea cucumber may process several times its own body weight in sediment. In areas where they are abundant, entire stretches of the seafloor are reworked, oxygenated and fertilized through their activity. Their feeding helps prevent the buildup of organic sludge that, if left unchecked, can lead to hypoxic conditions. But sea cucumbers are more than nutrient recyclers. Their role in benthic food webs is layered. They are prey for a variety of animals, sea stars, fish, crustaceans, and in some areas, humans, who harvest them in large numbers for food and traditional medicine. Yet the sea cucumber is far from defenseless. When threatened, many species can expel their internal organs through a rupture in the posterior body wall, ejecting sticky, fibrous threads known as Cuvierian tubules. These tubules can entangle or distract predators long enough for the sea cucumber to escape, or more realistically, to not be eaten immediately. Some species add an extra layer of deterrence. The expelled organs are coated in toxic compounds, including holothurin, a detergent-like chemical that can be lethal to fish and irritating to human skin. The organs are later regenerated, a remarkable display of physiological resilience. This evisceration defense might seem extreme, but it highlights a fundamental truth of sea cucumber survival. Their best strategy is to make predation inconvenient. They cannot run, they cannot fight, but they can make the effort costly. In some cases, predators will abandon the attack entirely, distracted or confused by the sudden mass of sticky entrails. For an animal that appears defenseless at first glance, the sea cucumber carries a surprisingly sophisticated array of biological tripwires. Their bodies, though soft to the touch, are reinforced by microscopic ossicles, calcareous structures embedded in the skin that provide structure and, in some species, mild protection. Their water vascular system, inherited from their echinoderm lineage, controls locomotion via rows of tube feet that operate through hydraulic pressure. Though they move slowly, often imperceptibly across video footage, they're far from passive. Some species exhibit nocturnal behavior, emerging from crevices at dusk to feed under the cover of darkness. Others, like the swimming sea cucumbers of the deep sea, have evolved fin-like appendages that allow them to rise from the seabed and drift to new areas, using ocean currents to expand their range or escape threats. Perhaps the most unexpected dimension of sea cucumbers is their role in maintaining coral reef health. In reef systems where they are abundant, their constant sediment turnover helps maintain the delicate balance of nutrients that corals require. By processing sediment, they reduce the amount of organic material that can lead to microbial blooms, events that strip oxygen from the water and weaken coral resilience. In this way, sea cucumbers act as stabilizers, preventing environmental tipping points that can cascade into broader ecosystem collapse. Remove them, and the balance can shift toward decay. This ecological importance is now under growing threat. In many parts of the Indo-Pacific, sea cucumbers have become the target of intensive commercial harvesting. Highly valued in traditional Chinese medicine and cuisine under the name bêche de mer or trepang, they are often dried, packaged, and sold as luxury health foods. The most sought-after species can fetch high prices, driving overexploitation even in protected marine reserves. Because sea cucumbers reproduce slowly and rely on synchronized spawning events that require certain population densities, overharvesting can devastate their reproductive viability. In many reefs, once abundant populations have collapsed, with visible effects on sediment quality, algal overgrowth, and coral health. Their reproductive strategy is both simple and fragile. Most species are broadcast spawners, releasing eggs and sperm into the water column where external fertilization occurs. Timing is critical, often coordinated with lunar cycles or seasonal cues. Fertilized eggs develop into planktonic larvae that drift for weeks before settling to the bottom and undergoing metamorphosis. But without sufficient adult densities, these mass spawning events fail. It's a biological bottleneck that makes population recovery especially difficult. And yet, in areas where sea cucumbers remain, their presence is unmistakable to those who know how to look. Trails of processed sand mark their routes. Cleaned sediment differs in texture and appearance from the surrounding silt. In some tropical lagoons, dozens of individuals can be seen spaced across the bottom like a quiet cleanup crew, each working an invisible shift in the ongoing maintenance of the marine environment. They are not glamorous, they are not loud, but they are essential. In the larger context of ocean life, the sea cucumber represents a different kind of power, one that does not dominate through force, but through function. Its influence is not immediate or obvious. It doesn't kill, it doesn't chase, it doesn't stun. Instead, it stabilizes, it purifies, it recycles. It is the immune system of the benthic realm, the shell fortress that doesn't need walls to defend itself. Its only offense is making the space around it cleaner and more difficult to claim for those who would poison or overwhelm the seabed. And in doing so, it shapes the battlefield for every other species that lives above or around it. The sea cucumber teaches us that not all warriors wear armor or wield fangs. Some protect by sifting through the waste, quietly building resilience from the ground up. In a world of predators and prey, ambushes and escapes, it reminds us that ecosystems are only as strong as the soft-bodied engineers holding the foundation together. Beneath the cold surface and into the silences of the ocean's edge, nature refines its tools not with uniformity, but through divergence. Across 9 species we've followed, spanning muscle, mind, poison, partnership, and stealth, the shape of predation takes wildly different forms. From the stillness of the reef floor to the thunder of sonar in pitch-black depths, every predator becomes a reflection of its habitat, each one shaped by pressure, whether thermal, ecological, or evolutionary. But when laid side by side, these predators reveal a tapestry of tactics. Each is a specialist, and each represents a unique solution to a shared challenge: how to kill, feed, and survive without being killed in turn. In raw predation style, few strike faster than the seahorse, whose suction-based feeding is one of the fastest movements in the animal kingdom, faster than a blink, with no chance for prey to dodge. But if speed is a weapon, penguins wield it with precision, hunting in groups and using agile turns, pressure dives, and bubble trails to confuse and corral fish. Sperm whales deploy a far less visible tool, focused sound. Their prey, often giant squid, is not chased in the traditional sense. It is found acoustically, stunned with sonic blasts, and consumed in the dark. The stonefish, in contrast, hunts by becoming the background itself. It does not chase or ensnare. It lets gravity and illusion do the work, striking with a twitch of the jaw once its prey gets too close. Sea otters defy the usual predator mold. They don't pounce, poison, or ambush. They open. Their role is surgical, breaking through the exoskeletons that defeat others and using tools in ways that make them one of the most cognitively advanced hunters in their niche. In sheer power, however, the walrus reigns. It uses weight, tusks, and numbers to dominate territory, stir up the seafloor, and fend off polar apex predators. The sea anemone, fixed in place, resembles none of these. It is a floral sniper, waiting, stinging, immobilizing with microscopic harpoons. It doesn't pursue, it disables. Its stillness is predatory in function. The sea cucumber too avoids the role of active hunter, but its control over its ecosystem is quiet and far-reaching. It consumes the waste of others and defends itself by weaponizing its own organs, turning viscera into deterrent. Its influence is not in what it kills, but what it prevents from decaying uncontrolled. When comparing sensory adaptation, the contrast becomes even sharper. The sperm whale is the undisputed sensory tactician. Its clicks travel miles, mapping three-dimensional worlds no light ever reaches. In the visual realm, the stonefish cheats detection with camouflage, so perfect it is often mistaken for coral. The penguin, meanwhile, uses motion, optical bursts of speed, rolls, and flash to outmaneuver predators like the leopard seal. Sea otters have sensitive forepaws that function like eyes underwater, able to feel the ridges of shellfish in murky kelp. The sea anemone lacks conventional senses altogether, but its tentacles react instantly to changes in pressure and chemical gradients. Even the sea cucumber uses touch and chemical feedback to understand its surroundings, not to hunt, but to decide when to eject internal defenses. The walrus depends on tactile vibrissae, specialized whiskers that map the ocean floor for buried prey, highlighting how touch, too, becomes a refined sense when eyes fail. Intelligence comes in many forms, not always visible. Sea otters show problem-solving and memory. They teach their young how to handle tools. They remember which rocks work best and store them. Their hunting is almost cultural. Sperm whales display social learning as well, sharing information across matrilineal clans. These are predators that don't just act, they plan. Penguins rely on group coordination, often synchronizing dives and managing risk as a flock. The seahorse and stonefish are simpler in behavior, but their evolutionary intelligence lies in design, energy efficient, foolproof, and repeatable. Walruses exhibit basic social cohesion and defense, and while they're not tool users, their herd strategies suggest long-term memory and collective learning. Even sea anemones and sea cucumbers, though devoid of brains, reflect biological intelligence in how their chemistry manages predators, parasites, and environmental stability. When it comes to defense mechanisms, the spectrum stretches from blunt force to biochemical sabotage. The walrus uses size and weaponry. Its tusks are both status and survival tools. Penguins use flight underwater, outmaneuvering threats in 3 dimensions. Stonefish don't flee, they discourage. Their venom, injected through spines, causes excruciating pain and tissue death, making them one of the few fish where touching equals risk. The sea anemone again does not defend, it eliminates. Its sting is preemptive and final. Sea cucumbers take the most unusual route, ejecting sticky, sometimes toxic entrails to entangle or repel predators, a strategy that is both costly and effective. Otters use social proximity and kelp anchoring to avoid drifting into danger, and have few natural predators due to their agility. Sperm whales rely on depth, body mass, and group defense. Bulls travel alone, but pods of females and calves will circle to protect the young. In all these species, defense is never separate from offense. It is woven into their design. Perhaps the most unifying comparison lies in ecological function. the hidden influence each predator has on the systems around it. Sea otters maintain kelp forest health by culling urchins that would otherwise devastate the ecosystem. Sea cucumbers regulate nutrient cycles, prevent detritus buildup, and indirectly support coral growth. Stonefish keep small fish populations in check, influencing reef competition. Sperm whales redistribute nutrients from deep waters to the surface with every dive, triggering phytoplankton blooms. Walruses dig and disturb benthic layers, enabling oxygenation and access for smaller organisms. Even penguins act as ecological couriers, cycling nutrients from sea to land through guano, which fertilizes Antarctic soils. The sea anemone provides both a predator role and habitat. Clownfish gain shelter, invertebrates hover nearby for scraps. Their presence stabilizes microreef communities. Even the unassuming seahorse plays a role, regulating microcrustacean populations and serving as bioindicators for seagrass health. Side by side, these 9 predators reveal no single evolutionary path, no dominant blueprint. What they share instead is diversity in form and efficiency in method. Some move constantly, others wait indefinitely. Some are giants with complex societies, others are stationary and brainless. But each operates with precision born of necessity. In the deep, in the cold, and under pressure, excess is trimmed. Evolution favors function over flash. And across all 9, one rule is consistent. Survival does not belong to the boldest, it belongs to those best tuned to their environment, in body, in behavior, and in role. This comparison doesn't reduce these animals to ranks or hierarchies. It expands the definition of what it means to be a predator. It shows us that lethality is not always sharp-toothed. Sometimes it's slow and subtle. Sometimes it's communal. Sometimes it's woven into the sediment. But always it's earned.